Hello, this video is a summary of curve sketching. It's basically applying all the techniques learned in this chapter. Now, the section before this video I did earlier because that's material I'll put on my first exam. But the main thing coming from the section 3.5 will be the idea of horizontal asymptotes. But everything else we'll be looking at kind of just taking a function and maybe applying everything to it, like critical numbers, relative min and max, like I said, asymptotes, maybe intercepts, and then using the second derivative information, points of inflection, concavity, and all that good stuff. So let's take a look. Now let's start out with one of these problems where it gives you the characteristics. So these can often be challenging for students because you certainly don't have any kind of function. You can type in a calculator and look at the graph. You have to get a general sketch based on information about the graph. Now the first thing it gives us is 3 points. So obviously those dots better be on your graph. 0, 0, negative 3, 2, 3, 2. So I come down here. And you can see my red dots there, 0, 0, negative 3, 2, and 3, 2. We have a couple of asymptotes, well, 3 asymptotes, two vertical, 1 horizontal. X equals plus and minus 1, so you see I drew those with the blue lines. And then a horizontal asymptote at y equals 1, so it's the purple line going across. So vertical asymptotes will break the graph into sections automatically. So that means with 2 vertical asymptotes, we're going to have 3 separate pieces. Now, the horizontal asymptote basically is just the behavior of the graph as it heads to infinity. So it's nothing more than showing that the graph's going to go near that value as you get toward infinity. The vertical asymptotes, remember, are discontinuities. We cannot touch or cross the vertical asymptotes. And what do we have here? We have f prime of 0 equals 0 and f double prime of 0 equals 0. Okay, we'll talk about that. Means we've got a situation where we're either going to get a point of inflection or a min or a max. It depends on what the behavior of the graph's doing around that point. But anyway, let's look at the left section here. So when x is less than negative 1, all the way when it's less than negative 1, we have an increasing graph. Okay. So if we know we have this dot at negative 3, 2, and the graph coming from left to right is increasing, so it would kind of slide along that horizontal asymptote, go through that point, and then go right up beside the vertical asymptote. So remember the graph behavior of vertical asymptotes, it's either going straight up or straight down, because basically they're one-sided limits as x heads to infinity. Left and right limits. So that you can never have a graph that just goes sideways and just parks itself right beside the vertical asymptote. It's either going straight up or straight down. All right, so there's the left section. Now in the middle, here's where we got to be careful. So you see we're between negative 1 and 1. So we're interested in anything that's between negative 1 and 1. And right here, what does it tell me? First derivative. F double prime of x is less than 0 when x is between negative 1 and 0, and then again between 0 and 1. And then again when x is greater than 1. So it means it's decreasing. First derivative negative means decreasing. So the fact that that's 2 separate sections, you might wonder why doesn't that just connect, because it's not like there's a vertical asymptote there or anything. It's separate sections because it's going to flatten out, and that's how we know we're going to have a critical number there, but it won't be a min or a max. That's how we know it's actually going to be a point of inflection. So the graph temporarily comes down, and it needs to flatten out to satisfy f prime of 0 equals 0. So it'll come down, flatten out for a second, and then keep heading downward. That's why it's not just one straight interval from negative 1 to 1. And then when x is greater than 1, the graph's decreasing again. So we know it has to run by the vertical asymptote, so it'll come down to the right through that point and then work its way along beside that horizontal asymptote. So that's basically the sketch. Now we can use the, since this one's a little more complex than the one I did in the previous section, the asymptotes and everything, I'd go ahead and take a look, even though I had mentioned that you don't necessarily have to use the second derivative info, but I would here to make sure it's right. This says f double prime of x is going to be greater than 0 when x is less than -1. Okay, that's true. That means concave up, positive second derivative. So that's true for that section. It's going to be concave up when x is between -1 and 0. That's true right here until it gets to that point. It's concave up. And then when x is greater than 1, it's concave up out to the right. But f double prime of 0 is going to be, f double prime of x is going to be less than 0 when x is between 0 and 1. So it means it's concave down between 0 and 1. So that definitely means you got 0, 0 as a point of inflection. Concave up, flattens out, concave down. Boom, we have it. All right, so we're going to take a function here and we're going to identify the asymptotes. Increasing, decreasing, relative extrema, concavity, inflection points, the entire graphing package. So right off the bat, we have two discontinuities that will go on our sign chart. Now we've learned in previous section, though, those discontinuities aren't guaranteed to be vertical asymptote. The rule is if they share a factor, another way you can think of it, if it makes the bottom 0 and the top 0, it would not be a vertical asymptote. That's probably the easiest way to do it. I often explain it as saying if they share a factor, like this has x minus 2, x plus 2, which the numerator would not factor. So in this case, that means both of those discontinuities are vertical asymptotes. But like I said, if you plug the number in, if it makes the bottom 0 and the top 0, it will not be a vertical asymptote. Notice the asymptotes are written as equations. You know, discontinuities you can express as a single number like this, that's fine. But vertical asymptotes are equations of lines, so they have to have a variable there. So x equals plus and minus 2. And you see I just kind of wrote the limit, the regular limit didn't exist. The one-sided limits would go to infinity. And from earlier, three limits at infinity, which like I said was, if you look at the videos for the first exam material, we can look at this, and the easiest way to do it was compare the exponents. Same exponent, so it's the ratio of the coefficients. 1 over 1 means 1. That's where the y equals 1 comes from. Well, all right, first thing I'm going to do is I'm going to say, let's find us some critical numbers. That could be fun while I enhance this. So we got to take us a little derivative there, don't we? So let's see if that's going to be a lot of fun there. I think that's going to be quotient rule. All right, bottom times the derivative of the top, which will be 2x. There it is right there. Minus top times the derivative of the bottom, which is also 2x, over the bottom squared. So you can multiply, distribute there, distribute here. Be careful because it all follows a negative. So you actually end up with a negative 8x minus a positive 2x, which makes negative 10x. And then what happens here, you have a couple of 2x, you have a 2x cubed minus a 2x cubed. So those cancel. And you're just left with negative 10x. So we set this equal to 0. And negative 10x equals 0, so x equals 0. Now, so we have three values on our first derivative sign chart. The 0, critical number, and those two discontinuities. Now, one thing to keep in mind, discontinuities will be on both sign charts, but don't assume, it could be, but don't assume this x equals 0 automatically will be on the next chart. Don't make that mistake. But the discontinuities absolutely will be there because they affect everything, the flow of the graph. So now we're doing the usual thing we've seen before. So like I said, this is kind of a review of the graphing technique, so nothing new here. All right, so there's my y prime. Got my test, there's my 4 intervals. Got my 4 test values, -3, -1, and 1 and 3. Plug them in here. And you can see over there, it goes positive, positive, negative, negative. Increase, plus, plus, minus, minus. That means increase, increase, decrease, decrease. And keep in mind that the discontinuities cannot be mins or maxes. Now at 0, we go from increase to decrease. So that's a relative max. So we have relative max at 0, f of 0. And the actual point then would be what? If you go up here and look at it and put in 0, you would get 1 over -4. So the actual y coordinate's -1/4. So like I said, it's not that difficult to plug that in there. I just generally write it like that, and if we need to plug it back in, we can. Okay, second derivative. So here I went ahead and rewrote y prime. Bottom times the derivative of the top, which is -10, minus top times the derivative of the bottom. Bring down the 2, change that to 1, and derivative of the inside, 2x. Now I let the 2 minuses be plus here, and the same factoring technique I've used in the other videos. In this case, you cross out the lowest exponent and then subtract the other 2 by 1. We've seen functions like this before if you've looked at the other videos or the notes themselves. You don't have to have seen the video to see this. So we kind of tidy up the numerator. So I kind of wrote it sideways this time. I don't know why I wrote the fraction sideways, but it's fine. So you would have -10x squared plus 40 right here. And then here you have 10x times 2 times 2x is 40x squared. So you combine terms, you have 30x squared plus 40. And remember to set this equal to 0. All we have to do is set the numerator equal to 0. And we get x squared equals -4/3. Therefore, there's no solution. Therefore, no possible inflection points. Only the discontinuities will go on our sign chart. So there they are, discontinuities, test values, -3, 0, and 3. Here's where I did it. I got plus, minus, plus. So we have up, down, up. So we already have, so keep in mind, yes, we are changing concavity, but you cannot have a point of inflection at a discontinuity. So the up to down or down to up only works if they're not discontinuities. Oh, there's an old sad face friend again we've seen before. And I sketched in the asymptotes by hand after I drew that there. So that looks pretty good. Well, we can look at the concavity while we're here. Concave up, down in the middle, up again. And so I'll say this verbally and then go back and look at the other sign chart. Increase, increase up to 0. So it's back-to-back increase. Then we have decrease coming this way, and then decrease coming that way. So it should have been increase, increase, decrease, decrease. There it is. That's terrific. Alrighty, here's that fractional exponent we got to watch for. You got to really, really watch for that. I sometimes have the toughest time getting students to pay attention to that. That's that needs to be your red light, meaning we're going to have that, two things. It's also going to be whatever's undefined in the first derivative and the second derivative. Either the first derivative will be a critical value, the second derivative will be a possible inflection point. So watch for that. Now we still could get, other values besides that, but that's going to be, so for sure, when you take this derivative, now I come down here and you see where I wrote that, you have the derivative is undefined at 0, but yet the original function is defined at 0. And that means 0 is by definition a critical number, but we're not through. We have to see if there's any others. So we take the function, I rewrote it like this with a positive exponent, set it equal to 0 to look for any other critical numbers besides 0. Okay, so I brought the 4 over, multiplied the x to the 1/3, then I divided the 4. So if you have x to the 1/3, you get rid of the 1/3, you cube both sides. That way 1/3 times 3 would be 1. So I've seen some people like to take this kind of problem and then take the 1/3 power. So actually, if you do that, that means that doesn't mean you found x. It means you've actually found the 9th root of x. 1/2 cubed, 1/8. We have 0 and 1/8 are the two critical numbers. Yeah, that's, I tell you, with those critical numbers so close together, well, let's just see if I did graph it. Yeah, I kind of graphed it there. I must have really had to spread out the scale a little bit because it would be hard to see unless you fiddled with the scale because they're so close to each other. You might not be able to see the patterns, that come from the chart there because they're so close. So we have 0, negative infinity to 0, 0 to 1/8, 1/8 to infinity. No discontinuities in this problem. I would not use a problem that has the fractional exponent and a discontinuity in the same problem. That's a bit too much. So I put in -1. I used 0.1 here because 1/8 is 0.125, so 0.1 fits in there. Of course, 1 will fit here. There's the sign chart. Minus, plus, minus. Decrease, increase, decrease. We have a relative min. Decrease to increase at 0, f of 0. Relative max at 1/8, f of 1/8. Okay, so now let's look at there's the second derivative. So I went ahead and took both the derivatives. Okay, so we'll just carry this derivative down to the next page. And there it is. Now this one, so as soon as you set this equal to 0, you'll find nothing. But we still have that same 0 that we had before that I explained in the other page, because we have the y double prime at 0 is undefined, yet it's defined in the original function, therefore it is a potential possible inflection point. But we got to check the concavity. So if you put in, like here's -1, I put in +1, I got negative, negative, that means it's back-to-back concave down. So no point of inflection, because we did not change concavity. It's hard to tell, but you see that curve bends a little bit, so it's concave. That's why I'm drawing the blue arrows indicating concave down. And then concave down again. But there's that, because you come down, you got a relative min at 0, and then it still goes decreasing, increasing up to 1/8, and then decreasing again. So there's that min, and there's that max at 1/8. All right, now we're up. So I guess I could have, kind of started with more challenging ones. Now I went back to an easier one. I guess I could have put this one first, but I'm not going to revise it now. So there's the two derivatives. Take the first derivative, set it equal to 0. And I get 0 when you factor this out, and this one's kind of a weird answer, but that's okay. Square root of 3/4, that's a real number, positive 3/4, plus and minus square root of 3/2. So we have three critical numbers, obviously no discontinuities here. So negative infinity to negative square root of 3/2, negative square root of 3/2 to 0, 0 to positive square root of 3/2, and square root of 3/2 to infinity. So here are my four test values. There's where I did it in the chart right there. And positive, negative, positive, negative. So positive, negative, positive, negative. Increase, decrease, increase, decrease. Increase, decrease. Relative max at negative square root of 3/2 f of that number. Decrease to increase at 0. So we have a relative min. And then increase to decrease at the positive square root of 3/2 right here. And that takes care of the first derivative information. So now here's the second derivative, so let's work with that. So we set that equal to 0, and pretty easy equation, x squared equals 1/4, as long as you realize plus and minus square root of 1/4, which will be plus and minus 1/2. So we have three intervals. And so negative 1/2 right there, positive 1/2. Test values negative 1, 0, and 1. I got minus, plus, minus right here. Concave down, up, down. So both of those will be points of inflection. Remember, there's not two different kinds of points of inflection. Down to up and up to down are the same thing versus the difference between relative min and relative max. So there are my 2 points of inflection. And there's our graph. The points of inflection are in blue. The critical numbers are in red. The min's at the extremum, relative extrema. So you see there are the 2 relative maxes right there, and there's a relative min. And the blues are the change in concavity. You see it's concave down right about to where the blue is, and then between the 2 blues it's concave up, and then it's concave down again. Well, I would assume this next one that I would use, let me see, yeah, I don't know, I just didn't mark it here, but I like these to be open interval. So these would be open interval if I had a trig one on a test. So we want one that definitely where the second derivative does not get out of hand here, and it does not. So the first derivative would be negative 1, and then the derivative of positive 2 cosine of x would be negative 2 sine of x. And then, so it looks like this one's kind of did a little bit different way. I guess I don't know, I just felt like doing it differently where I went ahead and, sort of set both of them equal to 0 kind of simultaneously, which we'll use the appropriate ones in the right sign chart. Before I was doing all the first derivative stuff and then all the second derivatives, except I might have taken the second derivative at the beginning, but anyway, so now take the derivative of this. So the derivative of negative 1 is 0, of course, and then negative 2 sine of x would be negative 2 cosine of x. Let's go back over here. First one set equal to 0, so I kind of use 2 different colors there to separate any confusion. So you get sine of x equals negative 1/2, so between 0 and 2 pi, you'll find that right here at 7 pi over 6, and then you'll find it again over 11 pi over 6. So those are CN, shorthand for critical numbers. So we have 2 critical numbers, and so you set this one equal to 0, so it just means cosine of x will be 0. That'll be at pi over 2, at 3 pi over 2. Remember, these don't really have an official name other than I call them possible or potential, either way, inflection points. So we don't know, they might be, they might not be. Now this time just to show something a little bit different for you here, which you just be careful. Now if you graph these functions, graph them in radian mode. But numerical values, I decided to show you that you could put your calculator if you wanted to in degree mode. And use degrees instead of radians. But like I said, if you're going to graph it though, make sure you're going to radian mode. Degree mode just doesn't graph very well. It just takes too much hassle to get it looking right. So I just put some appropriate degree measures here between those 2 critical numbers. Degrees, 90, 270, 345. I got minus, plus, minus. So I have decrease, increase, decrease. That means we'll have 2 extrema. A relative min, where it goes decrease to increase. It's going like this, down then up then down, like that. And then we'll have a relative max at increase to decrease at 11 pi over 6, f of 11 pi over 6. So I did the same thing here. Our 2 values, potential inflection points, are pi over 2 and 3 pi over 2. So that creates 3 intervals. So always remember, I'll do these problems as 0 to 2 pi. So in these problems, with regular variable x, we'll go with start at negative infinity and go to positive infinity. But these will start at 0 and finish at 2 pi for the trig ones. So there's the second derivative, and I use degree mode again. And Like I said, you just stick with radian mode. I guess I just felt like doing something different there just to show you. And let's see. And we get minus, plus, minus. So we have concave down, concave up, concave down. And that will, those possible inflection points are now officially inflection points. Down to up to down. And so we have 2 points of inflection. Stewie says something here. Stewie usually speaks to us in red, but okay, that's all right. So that's basically what I was saying a minute ago. You can read what Stewie says. Always use the radian mode for graphing. All right, I scaled this at pi over 6. I'm going to make that a different color. Represent the, let's see, oh. That's all right. And let's see, so you see it goes down, up, down, concavity. And that looks good. And we look at our mins and maxes and see how that looks. Okay, well, and we had the red, so the blue dots represent the change. Those are the pi over 2 and 3 pi over 2 for the inflection points. And there's the minimum, however many pi over 6s that is, 7. See, that was a common, see, between the 2 and the 6 here, pi over 2s and pi over 6s, 6 would be the common denominator. That's how I choose my scale. So that way, in other words, there's 7 pi over 6. So, in other words, 3 pi over 6 would be the same thing as pi over 2. And that's why this one will be 9 pi over 6. And there's 11 pi over 6. Here's another trig one. The derivative will be negative sine of x. Don't forget the chain rule here. The derivative of cosine of 2x is negative 2 sine of 2x. So therefore, the negative created by the derivative will change that negative to positive. And the 1/4, there's that 2 I was telling you about. Now I'll combine them together. 2 times that 1/4 will make 1/2. Of course, derivative of cosine will be negative sine. So we have this. And then the second derivative, the derivative of negative sine will be negative cosine. The derivative of 1/2 sine of 2x will be 1/2 2 cosine of 2x. Once again, same idea with that 2 right there. I guess I could have, I mean, not that that's mathematically wrong, but I guess that's sort of bugging me a little bit there. See if I can capture that. Could have put the 2 in front of that. That's okay. And these 2's then cancel. So let's work on the first derivative. Sine of 2x, to solve this equation, we just have to use identity, which will be on the trig sheet that I provide. That's pretty common, pretty easy identity anyway, but it's on that trig sheet. Sine of 2x will be 2 sine x cos x. And you see that cancels the 2's, but that wasn't the least of my concern. But now we do this, we need to get it down to be single angles. That's the whole key. So then that means I can factor out a sine of x, a common sine of x. That'll leave a negative 1 here, and then a cos x there. So you set each piece equal to 0. And then sine of x equals 0 from 0 to 2 pi will be pi. And notice that cosine of x equals 0, because I changed the problem to an open interval, 0 to 2 pi aren't really in the open interval. So we're not going to, they can't be mins or maxes. Well, they can be absolute mins or maxes, but we're not dealing with that. They're not going to be relative mins or maxes because they're at the end. And there's no other value between them that will equal 1. So in a way, that didn't really produce anything that we were going to be able to use. let's say if your interval, we've had problems like this before, where, let's say if it would have gone from negative pi to pi, then we would have used 0. That would have been a good idea to make it negative pi to pi. Anyway. Oh, the same thing here. Sine, we don't use sine of 0 or 2 pi. Yeah, that actually applies to both of these. Should move this one, make this at least a little bit. And then therefore that means those answers are eliminated. So pi is the only point of interest in that particular interval. Okay, let's see. Easy from this point on. Pick a test value. I used pi over 2 and 3 pi over 2. All right, did it right over here. Got negative, got positive, decrease to increase. We have a relative min at pi f of pi. So for the second derivative, I'm indicating this check mark, meaning we need to use this identity, double identity for the cosine. That's because there's a cosine here. Had there been a sine here instead of cosine, I would have used this last one. I don't think there's any need to use this first one. You're going to use one of these two. That's what dictates it, whether there's a cosine or a sine out there in front. Okay. Excellent. So then that leads me to, so these cancel these 2 cosine squared x minus 1 from the identity. There's a negative cosine of x. Now I rearranged it to put it in a quadratic type of form. These problems are generally factorable, and I certainly would make sure mine were factorable. I guess mathematically they don't have to be, but for ease of solving, I certainly would want them to be. And most book problems will make these factorable. And this one is. So you just kind of factor it like you're factoring a regular quadratic. It's just instead of x's, it's now cosine of x. That's the only difference. So it would factor into 2 cos of x plus 1 times cos of x minus 1. And you could pull all that out and check it. Set each one equal to 0. And we'll get cosine of negative 1/2. So we have on the unit circle, we'll have 2 pi over 3 and 4 pi over 3 will cosine is negative 1/2. And we have the same issue that we had a minute ago. The first derivative is the cosine of x equals 1 won't produce anything in that particular interval. So we'll just leave that alone. And what do we have? Let's do our sign chart. 2 pi over 3 and 4 pi over 3. We're looking for possible, those are the potential inflection points. Put in your test values. I don't know where I didn't put the chart this time, but that's okay. You can check that yourself, obviously. Negative, positive, negative. Down, up, down. Therefore, down to up will be an inflection point. Up to down will be an inflection point. So we have 2 of them. So there they are in blue. There's that. We only got one relative minimum. But see, from here, from the edge to the blue, it's concave down. Between the blues, it's concave up. And then after the blue to the end, it's concave down again. And only one minimum, though, because it's strictly decreasing all the way to here, strictly increasing the rest of the way. And I'm mentioning there that I scaled it by pi over 6. Well, that seems kind of redundant to have that on there twice, doesn't it? I guess I could put it. Maybe I'll bring it over here where you see it. Okay. So let's see what we got. Asymptotes, increasing, decreasing, relative. Only I'm asking for the first derivative only. Yeah, some of these get a little complicated, so I don't think I would get, worry about the second derivative on some of these harder ones, but that's okay. This will be good. So we got discontinuities at plus and minus 3. No horizontal asymptote because the power on top is larger than the one on bottom. All right, well, quotient rule, bottom times the derivative of the top, 3x squared, minus top is x cubed times the derivative of the bottom is 2x over the bottom squared. Tidy up the numerator, distribute the 3x squared, subtract off 2x, there's 2x to the fourth. You end up with x to the fourth minus 27x squared. So I need to set that equal to 0. So as always, only the numerator needs to be set equal to 0. So I factor out an x squared. I have x squared minus 27 equals 0. So if x squared equals 0, that means x equals 0. Obviously, there's no such thing as plus and minus 0. But there's certainly a plus and minus square root of 27. If you're having to handwrite this out, I don't care if you simplify the radical, but I always like to do it just so people can see. I'm not real picky about that. Square root of 27 is fine, but it's plus and minus though. But yes, that does simplify into 3 root 3. Wow, so we got a lot of excitement on this chart. First, we have 6 intervals on this one. Wow, impressive. Now you see the 2 dashed lines I drew to represent the -3 and +3. Those are discontinuities. So we do not want to make a mistake and call them relative extrema. Even if they change, we don't want to do that. All right, so, and then we have 3 critical numbers. -√27, 0, +√27. So I won't read out all those intervals, too much to read out. There are your test values. Let's see if I did them. Well, okay, I didn't show where I put them in there, but obviously, hey, go ahead and check it. You would need to. Obviously, I would have plugged these into the first derivative. I got plus, 4 minuses in a row, and then plus. So the first one goes increase to decrease. So I got a relative max at -√27, f of -√27. Decrease to increase, I got a relative min at √27, f of √27. And so I was only doing the first derivative here because the second derivative, I remember, got kind of ugly on this one when I did it before. But let's just look at the graph. Well, let me actually come back to the graph and look at this. This is good for you to know, I think. I mean, there's some stuff in Cal 2 that we don't deal with slant asymptotes, but we actually divide, do a bit of a variable division, so it doesn't hurt to take a quick look at this. You'll have a slant asymptote anytime that the power, it's still no horizontal asymptote. That's still accurate. But anytime that we have a larger power on top by 1 by exactly 1, the power is 1 larger on top than the bottom. So we had an x cubed on top and x squared on bottom. So that means we have what's called a slant asymptote. So you actually do a little division here. X squared minus 9 into x cubed. So you do it this way. You go x squared goes into x cubed, x times. Then you distribute. And remember, division, you're always subtracting going down. So you take x times x squared is x cubed. X times -9 is -9x. You're subtracting. So that makes this +9. 0 minus a -9 is actually +9. These are supposed to cancel. And then now you're done. That's once you had, if you had another division step, like if this was 9x squared, we would divide one more time. Because you're going to get something that's in the form of y equals mx plus b. In this case, just the y-intercept 0. There's no more division step. But anyway, so y equals x is the slant asymptote. So you see what's happening here is this, I graphed it, the red line. You see how the 2 blue graphs are running along that particular line? Yeah, if there is a slant asymptote, they'll ride along that line just as they would if there was a horizontal asymptote. So what do we have here? We got a relative max and a relative min. So we can go back and check and see if we got that right. Well, let's see. It goes increase, decrease, 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 increase. Hey, I remember that being correct from a while ago. Remember we had an increase, and there were 4 decreases in a row, and then increase. I'm not even going to scroll back up there because I know that's right. There's 2 vertical asymptotes. So we had a max, we had a min, and then concavity, concave down, concave up, down, up. So it should have gone down, up, down, up. Oh, we didn't do it. Okay, sorry. We didn't work that out. But you can see visually, though, down, up. Okay, yeah. We didn't solve that. I think this one, like I said, it got a little rude here. I didn't. Where's the original? Oh, that's okay. It's still the same problem. That's what it is. I'm just telling you I wouldn't. Okay, because yeah, I thought that was okay. I thought it was a new problem. But no, there's the first derivative right there for the one we just did. All right, so I said I'm not going to have you mess with something this bizarre. But anyway, let's just take a look at it. I'm not going to go through all these simplification steps. You can send me a message if you have a question or something. Anyway, but let's just match that. Then I'll match what I got on my chart there. So there's your numerator. We only have to set the numerator equal to 0. So 18x equals 0 means x equals 0. X squared equals negative 27 will not generate anything. So 0 is our only possible inflection point. Our discontinuities must be there, though. Again, remember those? The negative 3 and the positive 3, we're going to be there no matter what, whether we got the 0 or not. But the 0 is there. And just as I said a minute ago, before we looked at it, down, up, down, up. That's what this is getting with all the test values, down, up, down, up, down, up. But remember, those discontinuities cannot be points of inflection. So even though it's going down, up, like that, if those weren't discontinuities, we would have 3 points of inflection. But no, only one is 0 because it's got to be somewhere that's not a discontinuity. So that's the only point of inflection, 0, f of 0. And we'll close this section off with one of those delightful sketchograph with the following characteristics. I say delightful, but face-to-face class students don't often tell me it's not that delightful, but I like it. Makes you think. Ooh, there it is. Makes you think without having to be able to type in the equation. So we have 3 points. Let's see if those are on there. Got 0, 0, negative 2, negative 1, 1, 2, 3, 2, 3, comma 2. There they are. Asymptotes, plus and minus 1 for x. This looks real similar to the one we had before, doesn't it? That's all right. F prime of 0 equals 0. F prime of 3 equals 0. F double prime of 4 equals 0. So that means we've got we have 2 critical numbers and then 1 possible point of inflection. Now the critical numbers may not yield mins or maxes, but they could. But they're still critical numbers. So this says f prime of x is positive when x is between negative 1 and 0, and between 1 and 3. But let me look at this. So f prime of x is negative when x is less than negative 1. So I'm trying to look at this as it moves left to right. So it's coming down this way and comes on down like so. So it's got to go through your point. That's another reason that the point was up here. It would have to go up this way. But since down here, we know it's going to go by the horizontal asymptote and then also down by the vertical asymptote. And let's see what's going on in the middle part, between negative 1 and 1, which is broken up into 2 sections. It could have gone straight from negative 1 to 1 for the first derivative, but it goes between negative 1 and 0, the first derivative is positive, and then between 0 and 1, it's negative. So that means from negative 1 to 0, we're going up, and then 0 to 1, we're going down. So it should be a little downward parabola. There you go. Negative 1 to 0 up. F prime of 0 equals 0, meaning you got a critical number right there, which does turn out to be a max. And then you go down. Okay. And now, let's look to the right of 1. From 1 to 3, the derivative goes up. It's positive, so the graph goes up. But then greater than 3, it goes back down. So it increases and decreases. F prime of 3 is 0. So it goes up and then goes down. Now this part's kind of tricky here. Now, here's kind of where the second derivative comes into. Well, actually, because of the nature of the horizontal asymptote, it turns around. It can't do like it did in the middle. It's got to come down and then kind of flatten out beside it. But anyway, let's look at that's what this blue is going to be an inflection point. Because as it comes down, it'll need to kind of curl back up to flatten out, and then that's forming an inflection point right there. And that's the F double prime of 4 equals 0 part. Telling you that, oh, okay, potential inflection point, and there will be. But the concavity backs that up because it tells you F double prime of x is greater than 0 when x is greater than 4. So that means even though as it's flattening out, like this, it's flattening out, it's still concave up, like so. So the graph's decreasing, but still curved upwards. So that's a little sneaky right in there. So the rest of them should be concave down. X less than -1. Second derivative is negative, so concave down. From -1 to 1, strictly concave down all the way. And then from 1 to 4, it's concave down. So it starts here, goes to the blue dot, so that whole region is concave down. Then that little part right at the end makes it, when it flattens out, it turns back to concave up. And that concludes the video of the summary of graph sketching.